Hello, everyone. My name is Regina Gonzalez, and I will be presenting for my History and Philosophy of Science class, the final presentation. I will be presenting on Einstein's theory of relativity. Nope. Okay. Now, as an introduction, before we kind of get into the nitty-gritty of things, before relativity, physics and philosophy assumed time and space were absolute. But this was later challenged by the idea of relativity. Now, what absolute means, because we're going to be talking about it a lot, is that it's the end all be all. That is it. If I tell you that the sky is blue, then the sky is blue. That is the same for everyone there. It doesn't take into account people that are colorblind. It doesn't take apart people that can't see the sky. So that's kind of how physicists and philosophers assume time and space were before the theory of relativity came around. Now, for this presentation, my thesis statement is that relativity challenged the assumptions that space and time are absolute, and philosophical arguments challenge how science interprets experimental findings. Now, I'm going to get into that a lot more. Um, and to begin, we kind of have to go over what special relativity and general relativity, the things that go into relativity, are. Now, special relativity is Einstein's theory that he created in 1905, and it kind of is just it centers around a main idea. And that idea is that the laws of physics are the same in all inertial frames, and the speed of light is constant. Now, essentially, to break it down, is that it deals with objects moving at constant speeds close to the speed of light. That's what it means in kind of more understandable terms. Now, in special relativity is relativity of simultaneity. And what this means is, and this is a direct quote from our textbook, is that events that are simultaneous from a moving point of view are not simultaneous from a stationary point of view, and vice versa. Now, this kind of goes over two events happening at the same time. Special relativity shows us that simultaneity depends on the state of motion of the observer. Now, what that means is that if Jane is in a train and John is standing on a platform, they see two different things. They see things happening at the different times. Now, I'm going to give an example of this using those same two people and a train. And I think it's the most known example for relativity of simultaneity. And it's if Jane is on a moving train and John is on a platform watching the train and lightning strikes both the the front end of the train and the back end of the train, John, who's on the platform, will see them strike at the same time. However, Jane, who is in the moving train, will probably see the one in front of her. She'll see the light from the lightning bolt in front of her before she sees the one from the back. Now, what this kind of does for the theory of absolution, is that it kind of dismantles the idea of absolute time because, like I said, if Jane is experiencing the lightning bolt happening in front of her before the one in the back, then time cannot be absolute. Now, in special relativity, kind of building off of that is general relativity. Now, it extends the special relativity to include gravity, and it kind of uses it and describes it as in the curvature of space-time. Now, what space-time is the fusion of three spatial dimension and time. Now, what that means is that they're not just linked, like time and space are not just one thing together, but they're fused into a four-dimensional fabric called space-time. Um, and what space-time is that a lot of people can think of it as like a straight line. Now, massive objects such as planets and stars can cause space-time to kind of curve. Um, for example, if this is space-time, this pink, oh, put it right here. This pink line is space-time. And here comes in a big planet. It's going to cause it to curve, right? Um, and the curve affects the motion of the objects because, like I said, if it was straight like this, things can just um things can just glide along, right? Now, if the big planet is here and it's causing it to curve, then oh, I can't really show you, but kind of get the gist. It causes it to curve around it. Now, that is what general relativity is. That's kind of what how gravity is included in all of this. It doesn't just it changes what we think gravity is. It doesn't just kind of like add it. It changes how we view gravity and how we think of gravity. And this has some pretty deep philosophical implications. Because if space-time can bend, then space and time aren't fixed. They're not just there absolutes, but they're dynamic and they're relational entities. They're reacting to things going into them, like for a lack of better words. If a planet is intruding on a straight line, it's going to cause it to bend. So that means they're not absolute. That means that they're dynamic. Now, we're going to talk about philosophical assumptions a little bit more, and I think a good example of this would be Kant. Now, to see kind of how radical this shift is we'll take what Kant said. And he said, our intuition, but not determinations given for themselves, or conditions of objects as things in themselves, right? And that's from Critique of Pure Reason. And he's talking about space and time, and he's talking more so about how they're mental structures that we impose on reality. Obviously, if you think of space, they're just out there, right? Like we are deciding that they're out there. They're mental structures. Same with time. You can't really visualize time in that sort of way. You kind of think of time as a concept. And they're necessary for us to experience anything at all. Without space and time, then what's going on? Um, they're fixed forms and the same for everyone, but they're not discovered, but that they structure everything. And that's kind of what Kant believed, right? Um, so I'm sorry, I believe I am confused. No, Kant, the initial belief is that they were fixed forms and that they were the same for everyone, but that's not true. That's the whole point of absolution, and that's what relativity challenges. So that's going on to my next point is that the challenge that it shows space and time are relative to the observers and can vary with motion and gravity, just like we went over with the examples of space-time curving. Einstein shows that space and time are dynamic and relative. And as we know, that means different for each observer. Now, I think another philosophical issue is whether space-time is something in itself, like whether it's a substance that exists independently of matter. And that's called substantivalism. Sorry, I always get caught up on that word. And a definition would be the view that space-time exists as a substance independent of matter and gravity. I think Einstein initially learned it this way, but with going through and developing his theory of relativity, he ran into a trouble, which would be the whole argument. So, the whole argument is that Einstein assumed space-time points had identities apart from the metric tensor. Now, kind of to break that down is he imagined a region of space-time with no matter, a hole, and realized that if points in space-time had identities apart from the fields defined on them, general relativity would be indeterministic. And a good example of this would be the argument hinged on his tacit assumption, his meaning Einstein, that the points of space-time are inherently individuated, quite apart from the nature of the metric tensor field at these points. Only 2 years later, after other reasons compelled him to reconsider general covariance, did Einstein finally recognize the way out of his dilemma. One must assume that in an empty region of spacetime, the points have no inherent individuating properties, nor indeed are there any spatio-temporal relations between them that do not depend on the presence of some metric tensor field. Now, kind of just explain this a little bit more. I think the really important part is kind of the last sentence. I'm going to repeat that. One must assume that in an empty region of space-time, the points have no inherent individuating properties, um, nor indeed are there any spatio-temporal relations between them that do not depend on the presence of some metric tensor field. Um, Now, what a metric tensor field is um, it's a mathematical field of differential geometry. It's an additional structure on the manifold M that allows defining distances and angles. Essentially, what the metric tensor field is something that defines the two different points. Now, what Einstein is saying is that when it's all empty, space-time is empty, the points are not different from each other because it's empty. How can you differentiate one point from another if there's nothing there, right? And there's no spatiotemporal relations between them because it is empty, right? They do not depend on the presence of some metric tensor field. And that's the metric tensor field is what allows defining distances and angles from them. And that comes from John Satchel. Um, I think a good way, because it's all kind of getting in the weeds of science, is to just picture it as a puzzle board. If you have a blank puzzle board, you can't say that this spot is different from this one. Why? Because it's empty. But when you start filling in the puzzles, that's when you start to notice, okay, this point is different from that point. Why? Because it has more things in it. You can see that this puzzle piece is this far from this puzzle piece. So just to kind of reiterate, oh, I hope that that's not. Just to kind of reiterate, Einstein used to think that every point in space and time had its own identity. The problem is, if you can move everything and still end up with the same physics, those empty points can't really matter to themselves. So the conclusion is that points in space and time only become real or meaningful when something is there. The resolution to this problem is that Einstein adopted rationalism. Oh, sorry. Okay. Now I'm going to talk about the philosophical challenges a bit more. Um, and to get into that, we're going to talk about underdetermination and relativity. Now, what underdetermination is the epistemological ideal that multiple theories can equally explain the same empirical phenomenon. Essentially, what that means is that there can be multiple different explanations for data. And a good quote for this would be canonically, classic tests of general relativity, or GR, include perihelion precession, the bending of light around stars, and gravitational redshift. Modern tests have to do with inter alia, relativistic time delay, equivalence principle test, gravitational lensing, strong field gravity, and gravitational waves. Now, why this quote is important, why I chose to include this is because it kind of shows us, sorry, I hope that, okay, sorry, my camera was freaking out. It kind of shows us that general relativity has been tested in two main ways, which are old school tests and new school tests. Now, I'm going to explain those old school tests a bit more. Perihelion precession is essentially Mercury's orbit acting weird. The light bending around the sun is pretty straightforward. Gravitational redshift means that red light coming from strong gravity. So if there's strong gravity present, that means that red light will be present as well. Now, the new school tests are relativistic time delay, which means how gravity slows down time, equivalence principle, and whether all things fall the same way. Um, Gravitational lensing, which is how massive things warp space, which we were able to see with the big planets warping space-time, and gravitational waves, which is ripples in space-time. Now, they show that many of the classic tests confirming general relativity don't really prove general relativity at all. Other theories can predict these outcomes as well. And this kind of complicates the correlation that science has between truth and certainty, because how can something be absolute if there's multiple different explanations for it? And getting into those explanations, we're going to talk about them a bit more. Now, scalar tensor theories, they propose that gravity depends not just on space-time and curvature, but also on a scalar field that can vary. This changes the strength of gravity across space and time. Now, essentially what this theory is that it makes it so that gravity is mediated by both the metric and scalar field that makes gravitational constant vary. Um, it changes space-time dynamics while remaining consistent with observed solar system phenomena. So this is another reason that we could be seeing all these results that claim to prove general relativity. Now, TEVS, or what it stands for, is tensor vector scalar theory. It adds extra fields to the gravitational picture. So the tensor field, which is covered by general relativity, vector field, which is something with direction, and a scalar field is changing number across space and time. Now, these kind of fields adding to the gravitational pictures leads to different uh, leads to another theory to explain gravitational reasoning. Now, the last one is biometric gravity, and that goes even further, which is kind of talking about two separate metrics of space-time, not just one. And one kind of describes the usual space-time that we live in, and the second interacts in subtle ways. Now, all of these theories are here and differ from general relativity by changing how gravity interacts with spacetime. Each of these theories fit empirical data. This brings us back to the philosophical points of observational success doesn't mean theoretical truth, which brings me back to my thesis statement. Um, my thesis my thesis statement says it says, well, I'm going to focus on the bottom part. Philosophical arguments challenge how science interprets experimental findings. Now, without these other theories, without the influence of philosophy, we would not be able to challenge and think, okay, what other theories could be proving this data? Now, I'm going to talk a bit more about the philosophical interpretations. Now, just as like I said, empirical successes don't automatically confirm theory truth, right? All of the data from general relativity showed and were sorry, my dog is barking. Um, they all of this data was thought to prove gener, general relativity, sorry. Um, However, when you think about the other aspects, the other theories that could influence this, it makes it so you can't automatically confirm that that was general relativity. So the interpretation requires philosophical frameworks about what the tests measure. Now, they kind of show in these challenges, they show that philosophy isn't optional for science. Even the most rigorous empirical work must be interpreted. This undercuts scientific realism and highlights the need for philosophical clarity. Now, underdetermination shows us why. Multiple theories can be consistent with the data. So the choice between them involves deeper metaphysical commitments. Now, what that means is that without philosophy, we are not able to think deeper and think, okay, these are the facts of the data. Um, and since there are multiple theories, we need to think deeper. That is what philosophy helps us do. It helps us think clearly about what the evidence means and what it doesn't mean, what the tests are proving, what the tests aren't proving. And it kind of cautions us against assuming the experimental success equals truth. And it calls for you to double check your work and think, are there any other possible outcomes? Now, the way that underdetermination is connected to realism is just that it challenges it. Because if multiple different conflicting theories can equally explain the data, we lose the justification for saying any one of them must be true. How can one thing be so special if so many other tests have the same result? It shows that matching the data isn't enough to prove a theory is true, and that multiple theories can explain the same observation in gravity and relativity. We can't just assume general relativity is the final way, and that is how philosophy helps us. Now, in conclusion, Einstein's relativity fundamentally changes how we understand space, time, and causality. But it also depends on and challenges philosophical frameworks about reality. Now, it challenged essential metaphysical assumptions about space, time, and causal structure. Philosophy shapes general relativity's foundation and continues to refine its interpretation. The interplay of both science and philosophy safeguards against misinterpretation and enriches our understanding of reality. Now, from Kant's metaphysics to the whole argument to modern debates about realism, philosophy plays a vital role in shaping and interpreting scientific theories. And we often treat science as if it's the end all be all, as if it's just that's it, it stands alone. But that's really not true because, as we are able to see in relativity, philosophy isn't just a commentary, but it's a part of the foundation. Thank you for listening. Here's my bibliography. Um, and thank you so much.